Hello and welcome to this eCognition Deconstructed video. Today we're going to talk about the fill pixel values algorithm. This algorithm actually fills raster regions based on the domain by interpolating from neighbor object pixels. So this is actually suitable if you're having data sets with gaps and you want to interpolate into those non-data areas. And I'm talking about a raster image. And mainly this is used for elevation data sets like DTM, DSM or NDSM, but actually you can use it for any raster you like. It works on one layer, and that layer needs to be a temporary layer. So if you want to use this algorithm on imported layer, original layer, you first need to convert it into a temporary layer. You simply can use the layer arithmetics algorithm, for example, to do so. I'm going to show you that in a minute. For this algorithm to work properly, you need to create and classify objects that define the pixels to be interpolated. So you somehow need to classify the no data areas or the areas with pixel values of -99 or whatever, right? So you need to create objects that you need to interpolate into. Right? You simply can, for example, use the multi-threshold segmentation to do so. If your gaps have value of 0 and all the other values are higher than that, that's the fastest and easiest way to get there. So the algorithm parameters, first of all, the input layer. This is the temporary image layer that you want to modify, that you want to fill the gaps with information. Then the class filter that you set in the algorithm parameters are object classes with known pixel values. So this class filter describes the objects that hold information that you want to use to interpolate. Then calculation mode, we have actually two different ones: inverse distance weighting and linear interpolation. The third one is linear interpolation legacy. You can ignore this one. This one is just there because this algorithm changed at one point, and we want to make sure that also rule sets that were developed before that change are still usable in later versions. So that's why we still have this legacy algorithm there, but you can ignore that for now. And in the domain, you define the image object level and the class which represents the no data. Okay, let's quickly have a look at the difference between inverse distance weighting and linear interpolation. If you have a look at the figure on the right, the green pixel represents a pixel without information and want to interpolate into that pixel. If you use linear interpolation, eCognition simply uses 4 pixel values to estimate the value of the green pixel. So it goes into Y and X direction, and the first valid pixel it finds will be taken into consideration. So it sums it up, those 4 pixel values divided by 4, and then you have that pixel value. If you use inverse distance weighting, it also takes into consideration, this example, the gray pixels. So all valid pixels that are touching the object that you want to interpolate into, and then it also weights those information based on distance to that green pixel. So the closer the pixels with information are to the pixel that is interpolated, the higher the weight is, right? That simply means that if information is further away, it has a lower influence on the interpolation than information that is closer. Okay, let's have a look at an artificial example. If you go into the data folder, into the subfolder artificial gaps, you're going to find this project file, this DPR file, artificial gaps project.dpr. And simply drag and drop it into eCognition, and that's what you're going to get. So in the view settings, you see we have 2 layers. Layer 1, that was the original digital surface model layer. And I created an arithmetics layer, so a temporary layer within the project, which has gaps. So these blue areas are gaps. I filled those with 0 values, so no data. If you're interested to know how I did it, have a look at this section of the rule set. Fairly straightforward. The key is to use layer arithmetics, right? So have a look at this one here. But now we have this temporary layer that we need, right? And we have gaps that we want to fill. So first step is to create objects that delineate our gaps, right? or discriminate no data from data. And we're gonna use the multi-threshold segmentation. Create a new level. The image layer is the arithmetics, that's the one with the gaps. Threshold is 0, everything below 0 is gap, the rest is unclassified. Let's have a look. Right, the class gaps is already there in the rule set because I saved it in the project, and the red areas are now classified as gaps and the rest is unclassified. So unclassified holds our information. And now we're gonna use this algorithm that I've been talking about for the last 5 minutes. Fill pixel values. Now the settings here are important. First of all, input layer. Let's change this to arithmetics. Class filter, that's the class that holds the information. So in our case, unclassified. And let's keep it simple and let's start with linear interpolation. That's the faster one because it's just using 4 pixels to compute the value of a single pixel, right? And here in the domain, we define the gaps, so the class that is empty that you want to interpolate into. That's already it. So make sure the settings are correct, execute this one, and you see that something has changed. Let's undisplay the object level, and you see our gaps are filled with values. It worked very well up here. I'm going to display the outline. So up here it worked very well because the area is homogeneous. Down here it's a bit more difficult, especially at the border because it doesn't have information from the left. But actually did a pretty good job even in the slopes, and it was very fast. I'm quickly gonna reset it and again fill those areas with 0 values. So I'm removing the arithmetics layer, re-execute this layer arithmetics here, and then we should have the same layer again that we had at the beginning with the gaps. And let's see how inverse distance weighting does. Let's keep the weighting default and all the settings that we changed before, class filter, input layer, and here the class filter in the domain can stay the same. Execute it. And it takes a bit longer, but I think it did a better job up here in this valley area here, in this horizontal gap that we had, compared to the linear interpolation. Okay, let's have a look at a real world project where we try to interpolate a raster that is derived from a Lidar point cloud. So we want to create an elevation raster based on the information of a point cloud. So if you go into the data folder, into the subfolder Lidar interpolation, you're going to find the Lidar interpolation project DPR. Simply drag and drop that into eCognition developer, and then you should see something like this. It's a small subset of actually a project and rule set that's also available in our knowledge base. So have a look at the knowledge base. If you look for tree crown delineation, there's an advanced rule set looking at interpolation and also using this fill pixel values algorithm. And this data set, not a small subset as I do. But let's have a look. All right, we have RGB data. We have a raster called PC. This one is automatically created when loading a point cloud based on the intensity. So it always creates a raster which is connected to the point cloud. We also can have a look at the point cloud. You see it here. You can change the point size. You can have a look at the point cloud in 3D. So we have trees and background area here with low vegetation, and what we want to do is we want to create a digital surface model, so including the trees. How to do it? I'm not going to go into detail here. I want to focus on the fill pixel values algorithm, but you're going to have the rule set and it's split into linear and IDW. So you simply can execute the linear, and what this does, it rasterizes the point cloud based on the elevation information, so the C value, and then it does a multi-threshold segmentation and classifies the gaps. And that's what we need, right? We need a temporary layer and the gaps classified to be able to use the fill pixel values algorithm. And we created this DSM linear, and as you see, it filled the raster with information where we had a point in the point cloud, right? So you see here these points, and all the black area is no data because we don't have points there, and the raster resolution is fairly high, right? It's the same resolution as the RGB image. So what could we do to fill the gaps that we have segmented here using the multi-threshold segmentation? So red means gaps and the rest is unclassified. Of course, we can use this fill pixel values algorithm. And the settings here, again, on the left-hand side in the domain, define the gaps, like the objects that you want to interpolate into. On the right-hand side in the algorithm parameters, you define the input layer, DSM linear in our case, and we want to interpolate this one. The class filter unclassified. These are the classes that hold information that you want to use to interpolate, and the calculation mode is linear interpolation. Let's execute this. That's fairly fast, and in this case you see actually the artifacts, because as explained in the theory, it only uses values from X and Y direction, so 4 pixel values to interpolate the pixels, and this in this case results in these horizontal and vertical lines, these artifacts. It is very prominent here because we do have high elevation differences on a very small scale. Okay, so but that was pretty fast. Whoops. 0.094 seconds. Let's have a look at the IDW if that runs better. What I do here is exactly the same. I'm gonna rasterize the point cloud. I do the multi-threshold segmentation, and in this case I called it DSM IDW so we can compare the results. And now I'm gonna run the same algorithm, but simply what I changed is the calculation mode to IDW, and that's gonna take a few seconds, so you can grab a coffee and afterwards enjoy the results. Okay, so in my case it took 4 minutes 45 seconds. In the previous run it was faster. It's probably because I'm doing stuff in the background. Yeah, but what you also see here is some artifacts, and I think the reason for this is because we had way more pixels without information than pixels with information. And if we have a look at the object again, so red was no data, so actually to compute this pixel here, for example, here, it took all the pixel information that this highlighted object touches. So actually it's all pixels with information, and then it weighted them based on distance to that pixel, and it did it for all pixels without data. I mean, that sounds like a lot of work to do, which also explains why it takes way longer than the linear interpolation. However, I'm going to show you a quick trick how you could improve it. Actually, the results, I think they look better after the next approach that I show you. And also it's going to run way faster. So in total, this one, keep that in mind, 4 minutes and 45 seconds. Let's run the rasterize again and create the initial results. And what you could do is actually use the 2D, the pixel filter 2D. And as a filter, choose morphology. Input layer is this DSM IDW, output DSM IDW. So I'm gonna overwrite that layer, and the operation, instead of open, change it to delete, and that's gonna grow from the pixels with information into the surroundings. If we increase the iterations, it's gonna grow 3 times, and what this will do is it's gonna increase the number of pixels with information and decrease the number of pixels without information. Afterwards, the IDW is going to run way faster, and you're also going to see that the results look better. So delete, and you see everything that's white is now data, and black areas are our gaps. Then we run the multi-threshold segmentation, and you now see the red areas that have been all over the place at the beginning without that pixel filter 2D, now are focused on some areas, and now we can run the fill pixel values algorithm using the inverse distance weighting, right? That took previously 4 minutes and 45 seconds, and now the whole thing just, wow, it takes 0.15 seconds or something. It's quite an improvement. Let's have a look at the results, and the results, I would say, also look better than before. You don't have these artifacts, these pixelated artifacts, and actually you can rework, or could rework this result as well, smooth it a little bit so you can remove those pixel edges, and yeah, that's just a way to improve the processing speed. This idea was taken from a project and a rule set that is in our knowledge base that I mentioned before, which is called tree crown delineations. So if you look in our knowledge base for this tree crown delineation, simply search for it. You're gonna find a project and the rule set and input data that's gonna show you how you can interpolate Lidar data, Lidar raster, right? And that's where I found this trick, which I think creates nice results and is way better because the processing time was reduced by a factor of a few thousand. Okay, so thank you very much for watching. Try to use this fill pixel values algorithm if you want to close gaps in a DSM or DTM or NDSM or any other raster data set. It doesn't matter. You need to make the decision if it makes sense or not. Thank you very much for watching, and hear you next time.